Hi and welcome to the MSC Apex Iberian Lynx webinar specifically focused on the automotive industry. My name is Stefan Evans. I'm the lead FEA engineer with Evotech CAE Limited, a UK based reseller for MSC Software products, specialising in consulting, training and technical resales for all things to do with MSC Apex. This webinar was originally presented on January the 30th 2019 and has been re-recorded due to a couple of sound issues, so we hope you can hear us clearly now. So we'll get started. Apex for the automotive industry. Apex allows you to achieve a 10x reduction in model turnaround time, so massive efficiency gains both in terms of the power of the software and also the flexibility offered by very many of the functions in Apex. It makes the user experience enjoyable, so many users see Apex as very easy to learn, easy to use. Many people liken it to using a video game in terms of how enjoyable it is. It opens up the analysis process to non-specialists, so junior engineers and non-FEA specialists can become productive with Apex very quickly and perform many aspects of the FEA and CA model build task. It gives flexible license access across the MSC One licensing portfolio, so floating license availability and the ability to open up other MSC software technologies such as MSC Nastran, Mark and Adams multi-body dynamics. It integrates radically powerful FEA and automation techniques into flexible architecture, so many patented and novel technologies, direct modelling focused specifically for CA and FEA model build, generative model framework where any modification upstream is washed down, so we've got minimal user input, and we've also got a very powerful automation base using the Python technology built into Apex. These capabilities are very prevalent in the automotive industry, and we all know how important robust FEA is within that development process. Apex gives you the design freedom to develop your current and future products in a manner you have never seen before, and I want to sort of highlight that. The efficiency gains and the power of Apex means that you can build models, analyse and understand how a structure is going to work far more quickly and efficiently over anything else you've ever seen. The Apex journey. So early versions of Apex were easy to use, easy to learn. They were focused on a CAD to mesh type paradigm, so import geometry and then kick out a Nastran bulk data file. Then the software has evolved to include the Apex structures simulation environment, so you can actually go from CAD to results in a very rapid time frame, allowing rapid redesign and what if scenarios. Then the platform has been integrated and revolutionized with the advent of the Python automation technology, so you can automate black box and customize the environment. But then there's been a paradigm shift in terms of the way the Apex is developed and positioned to now include, for this release, Apex Iberian Lynx, the concept of gateway to Nastran through a series of interoperability enhancements. So now Apex can talk to Nastran both as a preprocessor and also as a post-processor. With Iberian Lynx, this is all now possible. So workflow maturity, so a legacy approach, Patran or some other third-party tool, both for pre and post, wrapped around MSC Nastran. As Apex has evolved, it came in as a companion tool, which means you can CAD to mesh effectively, then drop that into Patran or third-party tool as a preprocessor, and then onto Nastran and Patran again for post-processing. Then Apex is a full preprocessor, so you can do all of your model build, analysis and load case setup within the Apex environment, solve externally, but then still have to post-process in a third-party tool. But then now, where we are now with the Apex for Nastran functionality, we've got the capability to do full model build, full load case definition, full scenario setup, Nastran external solve, and then full post-process and result simulation within the Apex environment. Functionality growth. So going through this pretty quickly. So the early versions of Apex using the companion mode was that we had some keyword support from a CAD to mesh type operation, but then as Apex has matured, we've included more analysis setup and solution types, primarily by using Apex as a full preprocessor. And now with the advent of MSC Apex Iberian Lynx, where we can support all of the preprocessor phase and pretty much all of the post-processing and result exploration phase, we've got a much more full user experience and workflow. Result exploration, as shown, is increasing with future releases, and Orphan mesh control is increasing with future releases. Orphan mesh definition is where you work on a model where you've only got legacy Nastran bulk data file definition. You don't have geometry, so you need to use the original mesh as topology for subsequent updates and modifications. So how can Apex improve your productivity? Apex is now implicit in your MSC Nastran workflow. In simple terms, you can ditch your other third-party or Patran toolsets for Apex Iberian Lynx to become your main CAE workhorse. Apex is undergoing continual development in model build and manipulation, analysis and result exploration, with significant functionality improvements and enhancements with every release. Python-based automation environment now offers build, but also analysis and result exploration, which is new to Iberian Lynx, all enabled through the customizable user-defined tool and graphical user interface functionality. Apex's current and future development is driven by a desire to address key industry pains, allowing you to experience the full benefit of Apex-focused workflows. So we'll move on to a couple of examples focused specifically on the automotive industry, and I've tried to highlight models which will be of interest and highlight some of the capabilities that Apex has got. So just looking at this assembly brought in from a Parasolid CAD definition within the Apex environment, fairly complex, a number of parts, maybe 20 or 30 or so discrete parts within that. So Apex brings in the geometry and understands the full product assembly architecture, both in terms of parts and sub-assemblies. Looking at the lower control arm, we're going to focus on part of the model build at that level just to get started. So if you've never seen Apex before, just a quick intro to some of the model build analysis setup tools. So mid-surfacing operation, so we've pulled the mid-surface and calculated the equivalent shell thickness for that mid-surface. We're going to shell mesh that surface, show the elements that generated, and do a quick element quality verification on that definition. Apex has very powerful quality and model update tools. So we can see here we've got some invalid elements, very poor quality in certain regions, and we can see those highlighted. So the generative nature of Apex means that we can split surfaces, which in turn update the geometry, the properties, the mesh in a generative framework, and we can see that live in terms of the element quality check. So those elements disappear because they're now good quality, and repeat that for a second portion of the model. So we make these splits, and again, minimal mouse clicks, minimal form interaction, controlled pretty much completely from the mouse. We can now see we have good quality elements everywhere, or rather no poor quality elements, I should say. So this model definition is good to go. So one of the neat tricks within Apex is that we've got the ability to verify using the embedded Apex solver. So we can just look at the shell thicknesses first of all, an element normal check just to ensure that we've got element normal consistency. Obviously that's important given that we're using shell elements, and we can now verify the response of that single part within the sub-assembly using the Apex embedded solver, looking at normal modes, free analysis, run the solution very quickly, and see the influence that structure would have, just to make sure that it's tied together properly and responds from an analysis perspective as we so desire. And we can see here we've got for a free modal analysis we've got 6 rigid body modes and then 7 plus flexible body modes, and we can see that the structure is working as we would expect. So once we've got that part verified, we can quickly build the other parts through a mid-surfacing or solid mesh focus. We need to tie these entities together. So just tie these, we've got some welded entities at this particular component pair. So we've just used the Apex glue technology just to tie those together, and we can change the tolerances to better control those interfaces. We can use the concept of a joint definition to tie, in this instance, the pink region to the blue region using a revolute joint. We've got many different joint types in Apex. So just pick the entities at one end we want connected. So these will be the internal bores of the holes for the pink surface. So this is effectively generating a fastener stroke bearing interface to give us the Revolute behavior. So pick the solid face of the blue component, middle mouse button to accept. We've got the ability to modify the position and the orientation, but by default these are concentric holes, so no manual input used whatsoever, and we've got that joint defined. The generative behavior of Apex means that if we were to remesh or modify one of these pieces of geometry, then the resultant mesh and joint definitions and all connection updates or connection definitions will be updated. So just refining that mesh to a 2 mm on edge length, and we can now see that joint is still robust within that definition, and that goes for all entities or connection types in Apex. So running quick normal modes analysis, we can see that the structure is working as we expect, and we've got no moment transfer at the Revolute joints, and we can look at the strain energy distribution just to understand where some of those structures would see high stresses if it was a true vibration case. Then we can look at the static output, so we've got a pressure load defined and then some fixity constraints and a symmetry constraint, as we can see here. Run the analysis, look at the deformations, and then we can start to pull the discrete stresses out for the full structure or for the lower control arm that might be a region of interest, and then we can go through the design iteration loop to update anything we might need to. So pretty straightforward from a build perspective. So looking at the MSC Nastran workflow, specifically focused around Apex. So Apex is fundamental to your Nastran workflow by having enhanced Nastran keyword support for both model import and export. We've got MSC Nastran HDF5 results out interrogation, which means we can now read results in, and we've got powerful result automation, result exploration and automation capabilities. Quick infographic here just to show how, on the left hand side, how the number of BDF keywords are supported both for import and export within Apex. So Diamond by Python, shown in red, is one of the earlier releases, and Iberian Lynx is shown in grey. So the functionality enhancement or number of terms that keywords that are now supported has grown hugely across those releases. So we can now support coordinate frames, multi-point constraints, materials and properties, model definition, and loads and boundary conditions. Moving into the next workflow example, the chassis model. So we've got some simple, or rather some assembly geometry read in from a external CAD source. So the assembly architecture has been fully defined and respected within the model browser tree. We've mid-surfaced and manipulated those geometries to give us a more simplified version, and then looking at the underlying mesh, we can see what that structure would look like. We can show the equivalent shell thickness for those entities, and also look at things like glued contact. So again, because this is a meshless contact, we can build very quickly without having to ensure congruency of nodes and elements across the interface. We could ensure those congruencies if necessary, but we're using glue in this case for speed. So one of the sub-assemblies, we've got glue at the sub-assembly level, so we've got 4 cross braces and a cover plate, or a series of cover plates connecting those together. So once we've got that definition, we can now run the full job. Just a quick check on element quality. Massively dominated by good quality elements. We've got no invalid elements which would stop the analysis from running. We can now define our loads and boundary conditions and our boundary conditions and our loading environment. We can modify any of these at any given time, so we've got full flexibility based on the generative model description. Once we're ready to go, we can then run our external MSC Nastran analysis. So we create the scenario, which is effectively a load case, and then we can write that load case or a series of load cases out to the external MSC Nastran bulk data file for subsequent external analysis. We may have to use MSC Nastran from a certification or a client user base perspective, but once run, we can then attach the MSC Nastran HDF5 file format, read that in, and then we're into the post-processing environment that we need for MSC Apex, and we can fully understand the structural response in a manner that we couldn't do previously from an external Nastran run. Okay, so we're just looking at von Mises stresses for the shell elements and just understand the influence of the load case and where those stresses are going to peak. So looking now at an Orphan mesh workflow. So we're going to bring in the same bulk data file that we used for the original chassis representation. We can preview the model as it comes in, we can look at the number of keywords, we can change the unit system, we can specify how the model is going to be organised. So we're going to organise this model by what we call a contiguous mesh region. So each unique meshed entity has its own place within the subassembly architecture, and in the model browser tree we can see that. So just go to rendered mode, we can see a bit more clearly. So if we expand the model browser tree, we can look at discrete parts within that subassembly, or assembly I should say. And now we've got the Orphan mesh, so there's no geometry in this model. So what we're going to do is modify these structural members by first of all turning them into geometry. So we're going mesh to CAD rather than CAD to mesh. This creates faceted surfaces for planar, curved and doubly curved geometry. Very good control by default, but we've got user control, more involved user control if necessary. So we can go back into the model browser, post the full extent of the model, and see where those new faceted surfaces have been generated, and we can delete those mesh definitions where we don't need them and just retain the faceted geometry. So deleting those from the model browser tree, we don't need to do anything from a form or a user selection perspective. So the mesh has disappeared from those entities. So we just show only those entities to screen, and now we can manipulate those entities as we see fit. So what we're going to do here is introduce some lightning holes into the geometry. So we've got these cylinders we've already created using the sketch and 3D manipulation toolset, and punching out those holes in the faceted geometry, we can now remesh those surfaces with a much smaller element edge length. Again, good quality mesh defined very quickly and easily. We've got the shell properties retained from the original model, so we don't need to repropertize those entities. And now once we've got that topology definition built, we can use the glue connection, again a meshless technique, to tie everything together. Basically a series of explicit MPC equations behind the scenes, but very efficient in terms of connection and ensuring accurate load transfer across interfaces. So once we've got those definitions built, we can run the analysis and look at the response of the updated Orphan mesh region. We haven't updated the upper and lower plates at this stage, but we could have done. So just changing some of the scale the deformed plot scale options, running a deformation analysis, and then looking at the stress distribution for the entire model, and also for the region of interest where we've made those local changes. Again, so it's a very quick means of working with the Orphan mesh. Second approach, where we've created Orphan mesh for the original cross members, but we've also introduced some CAD geometry to have a mix of Orphan and CAD based approach. We've punched some holes in, we've got glued contact between the fine and coarse meshes, and we can now run that analysis again using the implicit Apex structure solver or the external Nastran approach, and see where we are with that structure. Very quick to do that in Apex. Apex sits well in terms of the Adams multi-body dynamics toolset, so there's an efficient workflow for that. So Apex can be fundamental in that MBD process. So Apex has the concept of analysis readiness, which effectively means that we can generate a valid FEA model very quickly and generate or create what's called the modal neutral file, the MNF file, for the Adams flexible body definition. We can generate the interface points as shown in the image on the right hand side, so that those interface points control how the model is tied into the subsequent Adams analysis. User can generate or verify the model behavior of the structure using the embedded Apex solver, and once that's been done, the modal neutral file, the MNF, is generated directly as an output from the Apex structure's normal modes analysis and can be brought directly into the Adams environment. The way that the modal neutral file is brought into Adams can be defined using an Adams plugin, and a quick overview of the process. So we start the Adams toolset, and here we can see for this suspension linkage we've got rigid body components shown in grey. We can then specify the Adams make flexible options and import the output generated from Apex. So go into the Apex environment and generate either the modal neutral file or a Nastran BDF file, and then read that information again back into the Adams environment, either directly as the MNF file or execute Nastran directly to generate the MNF file, associate the MNF file with the Adams assembly, and then the component is replaced with a flexible body for much more accurate multi-body dynamics and dynamic stress extraction within the Adams environment. Something that comes up quite regularly with Apex development, especially for automotive structures, is how does Apex deal with welded structures. So as Evotech, we've put together a 25-minute tutorial which covers a number of different weld modelling techniques: the nominal stress method, the structural hotspot method, and the effective notch stress method. And that's available at evotechcae.com, and follow the link through to the weld tutorial. Another weld example where Apex has become very useful is within the interface with another MSC toolset or technology, Simufact Welding, and this is run from a macro environment where the user is able to specify an assembly. This brings in some geometry and a CSV file of spot weld locations, some user input in terms of where those spot welds are going to be located. Bring the geometry in. The script is running with no manual input whatsoever. Meshing those entities, well, first of all splitting those entities based around the spot weld locations, generating the split lines, and then remeshing those entities. So we've got the detailed pink region on screen that's going to be meshed and then tied into the more global blue region with the appropriate element edge lengths for that resultant spot weld analysis within Simufact Welding. So again, big efficiency gain here in terms of using Apex in an automated approach to control the full model. So if we look at the resultant model definition, we can now see those spot weld local mesh controls for our subsequent spot weld analysis, and very straightforward to do within Apex. Some of the discrete enhancements that we've seen within this Iberian Lynx release: we've got a number of geometry enhancements. So we've seen this certainly in terms of lofting, but we've now got more mature, more evolved CAD type tools such as revolve, extrude, sweep, and lofting, which comes in very handy. So looking at this quick example, which is simple jet engine cowling. So we're going to look at revolving the curve at the front that we've just highlighted, and then spin that around an axis. So we're taking advantage of the Apex magic markers, which effectively allows us to pick things like endpoints and arc centers on the fly. Use the rotation axes. We've got full control in a manual sense, and we can see a preview of that surface, and then middle mouse button to accept, and we've got the front of the engine cowling revolved around to give us the surface on screen. So we've got the front of the structure built. So we're now going to look at lofting a surface, so picking a series of non-connected curves, and then building a surface that passes through those curves in a spline sense. We've got full control over edge continuity and what have you, edge tangency, to give us the structure that we want. Geometry from mesh, or the faceted surface creation, which we've looked at with a simple example. So we've read in a bulk data file. We've got no geometry. We can check the shell thicknesses and look at the topology. And what we're going to do here is modify the bulk data file to give us a solid mesh region. So conventional tools would be quite difficult. So what we're going to do is break out the shells in the region where we're going to replace them with 3D elements. Take the CAD out so we can see a hole in that mesh topology. So once we have the mesh that we want to work with, we're now going to create faceted surfaces from that mesh. So pick the mesh, middle mouse button to accept using the defaults in this case. It's built a whole bunch of surfaces created from those original shell elements. Of course, this could be done in an automation sense. We've got flat surfaces, but would work equally for curved surfaces. We've remeshed the structure using a new element edge length, and we've got full control now with this faceted surface geometry if we wanted to generate further modifications, so we can seed that surface if necessary. Key here is the faceted surfaces remembered the underlying shell thicknesses, so we don't need to repropertize. That's taken care of. So we dropped in a portion of 3D mesh geometry. We can glue those components together using the standard glue connector technology, and then run the model. So a very quick way to work with Orphan bulk data file definition and to modify that to modify or introduce new geometry as required. So some of the Iberian Lynx meshing enhancements. So we've got the concept of mesh diagnosis or meshability introduced in this level or this release. So if you look at a quick example of a tube interface, or a tube bracket, so we can 2D mesh that, or 2.5D mesh, hex mesh that, but some of the element quality isn't that great. So we're going to look at surface meshing these faces to drive the underlying hex mesher in the regions shown. Different mesh across different region. Now we can now see the fillet regions turned yellow, which means we're not able to mesh that. So we can use the diagnose meshability tool and see we've actually got a mismatch in the edge seeding in this region. So we can just match those seeds up, and the solid turns green again, which means it's hex meshable. We can hex mesh the whole thing, and we can do a quick check on the quality. So we've got a very good quality hex mesh defined very quickly using that mesh diagnosis tool within hex meshing. We can look at edge tie enhancements. So again, we're looking at this jet engine cowling. So we might have some internal stiffeners, which are in a separate part, sub-assembly within the Apex framework or model database, and we can see that we don't have mesh congruency at those interfaces. Still maintaining the unique part definition. So rather than merging all these into one part, we're keeping them separate. But obviously we need to use the concept of the edge tie to tie these discrete regions together. We can do that. Just wait for the mesh ties, and then now the meshes are tied together between those discrete parts within the sub-assembly or assembly architecture. We look at the edge tie on its own. So for Iberian Lynx, the big change here is that we can now mirror, transform, modify those edge ties as a function of the total model. So we're just going to rotate that model round or mirror that model round, and then look at the resultant edge ties that are generated. So it's mirrored the edge ties as well. So we've got full mesh control at that level, and then we can run analysis for the fully tied model just to show the local behaviour. Incremental surface meshing, and then some of the shell orientation modifications have been introduced. So we can look at in this quick example, so we've got 4 holes in the surface. One of the holes is very close to one of the edges, so the standard feature mesh definition has not been defined for the hole near the edge. So using the incremental surface mesher, it will mesh the features as it sees them. Here it's found the hole, it's shown it in red, it says we can't fit that washer in, so we can change the washer width, so just decreasing that for that single region, and then remeshing the whole structure, and those features are preserved within the full mesh definition. We've got the ring of elements as required. One thing which is very important in an aerospace environment, especially if there's going to be downstream hand calcs, is to ensure element alignment for a given region. So we've got shell elements here with the x-axis originally pointing parallel with the long edge. We're changing those now so they're all pointing parallel with the shorter edge. So just a simple rotation of those element XY orientations to make sure we've got element consistency or result consistency in those XY directions. Nastran interop enhancements. So we've got ID management, the ability to renumber entities, coordinate system definition. We've got discrete ties now fully supported, so that's RB2s and 3s. So we can look at this quick example. So we've got, again, this tube into bracket scenario. We've got the hex mesh as shown, and then we've got a bar element representing the tube with its equivalent section shown now. We can use the renumbering, so we're going to renumber the nodes and elements for the hex mesh region, or the hex mesh part within the assembly. Accept the defaults there, and then we look at the exported bulk data file and look at the element and grid IDs, and they're shown in the 10,000 series as defined. We can create coordinate frames explicitly, so we're creating a cylindrical coordinate frame at the parallel with the axis of this tube and defined at the central point of the tube. Once we've got those coordinate frames defined, we can renumber if we wanted to. We can apply loads or boundary conditions. So here we're constraining the internal faces of the tube in the radial system, or the radial direction of the cylindrical coordinate system. So just picking out the faces. Again, very quick to do that with an Apex environment. Middle mouse button to accept, and we've now got that boundary condition defined. We can use a discrete tie, so we've got rigid RB2 or compliant RB3. So pick the faces of the geometry, and then pick the center point of the bar element, or the endpoint of the bar element. It creates those ties explicitly. And again, this is generative, so if you just change any dimension within the model, the mesh and those tie and even those coordinate frame definitions will get updated. So we can post-process in that local system. So just changed to an externally defined coordinate system, and then we can look at the R, theta and Z displacements. Vectors are shown on screen now, and we've got full control of that coordinate frame definition. We've got the concept of joints within Apex Iberian Lynx. So rather than building manually coordinate frames, local grids within particular coordinate systems, and then tying all those together with RBE 2 or 3 elements, we've now got the concept of joint, which effectively does all of that type of build and connection within a single Apex environment, or a single Apex function. So here we're building an involute joint, which is effectively allowing rotation about the axis of connection and connecting the shell structure into the local bar structure. And again, those entities are developed in the model browser to see the specifics, or to modify the specific if necessary. If we look at the resultant BDF file that's written out, we can see the local grids, coordinate frames and connectivity that's defined, and obviously the Apex solver gives us that response as required. We've got result exploration, so we've got the ability to import Nastran HDF5 result files to probe those results using 0D and 1D probes to develop scalar vector or tensor plots at particular locations, or even over a path or a curve drawn on a model or mesh. And then finally, within this Iberian Lynx release, we've now got the ability to write out those results to an external CSV format, and we can just look at this this structure to show how we could export the bulk data file. And we can look at the bulk data file that's created. We can do this on a single file or an include file definition. We can run the Nastran result or generate the Nastran results externally, and then read that HDF5 file back into the Apex environment. Just bringing that in, importing the results, and the results are brought in successfully. And we can now post-process. So we're going to look at a quick animation of displacement, and then we can look at discrete results. So in this case, we're looking at the beam element section outputs based on the combined axial and bending stress, and then we can look at using the 0D cursor, so we can pull out discrete results. And again, this is very visual, so you can, very difficult to make mistakes when you can see the output explicitly. We can generate a table of those probe results and modify the table if we need to, and then write that data out to a CSV file for external post-processing if we need to. Some of the Iberian Lynx customization and automation enhancements. So we've now included scripting support for both analysis and result exploration. Previously we only had it for model build, but now we can effectively black box the whole process by including analysis and result exploration. We've got the ability to custom develop or custom define tools within the Apex environment, as we've seen with one of the earlier examples looking at fastener build. We're just going to look at this quickly. So here we've got a simple example, a simple macro which defines the geometry of a buckling panel under compression. So we can run that script, and we're handling the model build, so mesh, geometry, mesh, properties, loads of boundary conditions, but we're also invoking the Apex solver and result exploration through that automated approach as well. So we get all the way through from a single click of a run script button to having results in the environment with no manual input whatsoever. So this opens Apex up to parametric studies and or the ability for less experienced engineers to take advantage of the full FEA model and analysis capability. So we're just looking at some of the buckling modes here, and we can see we've got a low buckling mode shown in red in the table on the right hand side, and if we wanted to, we could rerun the analysis to look at different design setups. So second scripting example here. This one introduces the concept of the custom tool environment. So we've got an Apex script set up, and the custom tool is set up to read that in by the graphical user interface. So we've got a family of parts here, so we could effectively define this based on all sorts of different dimension and model criteria. But once we've got the inputs that we're happy with, we just press the green button to accept the inputs, and then the model runs, or the macro runs and builds the model. So we've got a sort of flexible tube arrangement here. So building the geometry, so sketch and then revolve that round, mesh the structure, and then we've built the model completely. And then we could have in fact included the analysis and result exploration within this script, but we can see the model response based on those initial parameters. So once we've got this defined, we can we've got full control of the model. The key thing here to say is that Apex really now is a game changer. There's multiple technologies in the Apex environment, which mean we've got a model build, solve, analysis, solve and post-processing capability unseen of before in terms of legacy tool sets, and really now it's open to you to use and to take full advantage of that technology.